G'day YouTube, Warbles on a lot here. Look at this. What you are seeing is water being sucked up a tube. Already the water has climbed about 1.5 feet and it's still climbing. As you can see, it's continuing to climb. What's going on here is that part 1, line 1, we have a cloud across the sun. And that's been getting sort of thicker in waves for a while. Part 2, line 1, we're starting to get tree shadow onto the dish. So therefore, the canister is cooling down. And effectively, when there's 1.44 pounds per square inch of vacuum inside the gasification canister, then that's when the water will rise all the way up to the top of the tube, which is 3 feet high, and 1 atmosphere of water is 33 feet, i.e. if you go scuba diving or skin diving and you're breathing pure oxygen, once you get to 33 feet, you've got 2 atmospheres of pressure and you go mad. Oxygen psychosis, they call it, just like nitrogen psychosis. Down to the depth of 33 feet, there lies a devil called Oxygen Pete, is what they used to sing back in the Second World War when the British were inventing oxygen boosted rebreathers. So anyway, point is 33 feet of water is 1 atmosphere, and once this thing gets up to the top there, it will have climbed 3 feet, so 1.45 pounds per square inch of vacuum in the tin after the entire day's activity. And you know what? It's still climbing, and if I let it continue to climb, it will contaminate the fluids that are in the jam jar, and I can't let that occur. So around about now, I have to disconnect. Couldn't wait any longer. Previous days on earlier runs, I've reconnected this, but all that I've succeeded in doing was to completely contaminate my fluid trap jar. So I'm going to disconnect that, and therefore, thus and because, I will be able to accurately measure the amount of liquid which has been driven out of the feed sample, which was today the amount of 100 grams, or 99.9 as it says there. There we go, yeah. Varies between 99 and 100. Scale can't make up its mind. All chopped up into little pieces. And would you believe, last night I made a video about the previous day's run, And there's a comment on it from a mate of mine, VB Ed, Yay Team Coopers. And he asked me, what's the goal of this series of experiments? What am I trying to achieve? Well, you see, Ed, it goes like this. Normally I could show you the outside fire, which sits there on them 3 bricks. Over the past 20 odd years, the outside fire has succeeded in producing a considerable amount of charcoal. But to produce that charcoal, I had to set wood on fire. And when you set wood on fire, you produce carbon dioxide. And forgive me for quibbling, but while it's good to produce carbon so that you can put it back into the soil, we have a bit of a problem with carbon dioxide in the sky. So I don't know whether you've noticed, but I'm kind of surrounded by a forest, and a functional forest drops a fair bit of wood on the ground, and either I treat it the way traditional Aborigines treated wood and I burn it off, but if I do that, I have trouble with the sacred fence fantasy, because if you let a fire go across your neighbour's boundary, you're financially responsible for all the damage that fire does. Or I figure out something else to do with all of that otherwise bushfire fuel hazard lying on the ground. And it occurred to me that all you really have to do to turn wood into charcoal plus methane and hydrogen, and they're pretty clean fuels, all you really have to do is heat it. So why not use the sun? And a repurposed satellite dish as a solar thermal reflector to heat a canister of wood. And this thing, it's 0.39 of a square metre. So at 100,000 square centimetres to the square metre, there's 3,900 square centimetres of mirror surface there. And it's all focused on about 63 square centimetres of the bottom of a ½ litre paint tin, which is 9 centimetres across. So what you're looking at is a 61:1 step-up ratio, which means that on a clear blue sky sunny day, there's about 5.5 watts per square centimetre across the bottom of that tin can. The thing is, it's not actually distributed evenly. There's a very small area, about maybe 5 or 7 square centimetres, which has a very, very high temperature. And using my thermo probe, I've been able to discover that sometimes that area is, as high as 674 degrees Celsius, which, by the glories of the conversion calculator, is 1,245 degrees in fairy farts. Foreign whatsies, them things that the Americans still use. Fahrenheits. 1,265 degrees Fahrenheit. 674 degrees Celsius. But that's all only on one little spot on the very bottom of the can. The rest of the can is cooler than that. Sometimes the edges of the can are like 300 degrees cooler than the central hotspot on the base, which is why I have found that not only is it necessary to have a double layer thermal insulation, quote, tea cosy, the tea cosy has to extend down below the level of the base of the can. And on this one, it's a double layer tea cosy. All the heat leaks have been sealed, as you can see. So I've done the best that I can conceivably do at keeping the heat in. However, when it was 500 degrees on the bottom of the tin can, and I have stuck a thermal probe in there, like at the moment, it's still 54 degrees and climbing. Just from whatever heat there is in the shady kind of sunlight which is hitting the bottom of the can at the moment. But it was as high as 100 degrees at the top on the outside of the canister inside the insulation. 100 degrees Celsius, that is, boiling point of water. Now, if we're really generous and we estimate that it's going to be twice as hot inside the tin as outside the tin, so it would be 500 degrees at the bottom inside it, 200 degrees at the top inside it. The average temperature inside the tin is about 350 degrees Celsius. And there's a steep heat gradient from the bottom to the top, which is why the wood that I took out of the canister yesterday was only about 30% carbonised, you know, like, and it was the bottom end that was carbonised, it was the hot end. I have to do something to get more heat into the canister from the outside of the bottom surface, and I have got a pretty good idea of how to do that. But at the moment I have 1.65 litres of syngas in the gasometer. Most of the cloud that was kind of troubling me has gone away. It turns out that a 100-year-old red stringy bark can produce 3.75 litres of burnable gas per 100 grams, even when it's not getting enough heat. So my plan is to crunch the numbers and draw the graph and drink a bit more beer while waiting for the sun to go down so that I can show you what 1.75 litres of stringy bark solar thermal concentrated synthetic gas flare off looks like. Warbles on a lot to YouTube. Until later. The mad scientist experiment continues. Oh, and by the way, the reason why I think this is worth doing is because in 1944 my father built a charcoal gas producer for his car, and he used to take the family to the coast, which is 150 miles away, and then drive home. Admittedly, he had to use petrol to go back up the hills. But anyway, I figure this is worth doing, especially if I can do it without burning between 25% and 50% of the feed stock in order to generate the heat to gasify the rest of the feedstock and convert the wood into methane and hydrogen and put the carbon back into the soil without burning anything. Maybe I'm going to need 15 square metres of mirror and 20 litres of container and, I don't know, 5 kilograms of wood. But if that'll produce 300 or 400 litres of gas per day, that would run this for about a half an hour. Or it would run this all day and more. And as it happens, I've got a pretty good idea of how to transfer more energy from the outside of the bottom of the can into the inside of the middle of the can. So maybe I can get 1,000 litres a day out of 5 kilograms of wood with which to run the generator for an hour and a half, while emitting a quarter of the carbon dioxide it would running on petrol, which I can't make here on farm. So, at the end of the day, 100 grams of 100-year-old red stringy bark yields 33 mils of water, tar and creosote from what was 100 grams. And maybe as much as 50% of the wood has been carbonised. $40 grams of it anyway. Let's say 40% has been carbonised. 33 mils creosote and tar, 1 litre of vapour, 3.75 litres of syngas, 39.9 grams outgas, 33 mils, 6.9 grams of gas and vapour, 5.38 grams of syngas. So it's just not hot enough. If I could get 50% more heat into the can, I could turn twice as much into gas, aka 80 to 90% of the wood volume. Carbonised would make 3 times more gas. So there's today's graph versus yesterday's graph with both of them together. So here's the burn. Ciao.